Section 8.5 is partial fraction decomposition. Have y'all ever seen partial fraction decomposition? Do you know what it is? No clue. Okay. Well, then I'm going to go through example 1 and show you how to do partial fraction decomposition, and then we're going to go into it in more detail. Basically, what partial fraction decomposition does is it takes a fraction where the denominators are written as factors, either linear or quadratic, and it allows us to rewrite this as a sum of two fractions where I have a over this first factor, linear factor, x plus 3, plus b over the second linear factor, x plus 8. And this is helpful for rewriting the integrand of integrals because it makes it easier to integrate the problem. The goal of partial fraction decomposition is to find a and b so that this expression on the left is equal to this expression on the right. And that way we could rewrite an integral and make it easier to integrate. So how we do that is we've set up an equation here, and I'm going to multiply both sides of the equation by the least common denominator to eliminate the fraction. So that means that I'm going to take the least common denominator, which is x plus 3 times x plus 8, and I'm going to multiply both sides of the equation by x plus 3 times x plus 8. And when I do that, both of these factors are going to cancel with these, and that's going to leave us with 13x plus 69 equals, and then when I distribute this least common denominator across to this first term, the x plus 3's are going to cancel out, and I'm left with a times x plus 8. And when I distribute the least common denominator to the second fraction, I'm left with b times x plus 3. So now I've created an equation, and I want to plug in numbers for x and solve for a and b. And what I'm going to do is I'm going to create a system of equations. And I do that by picking numbers for x to b. Typically, you want to pick numbers where these factors are going to go to 0. So let's say that if x is equal to negative 8, then we're going to plug in a negative 8 here in place of x. And I get 13 times negative 8 plus 69 equals, this term is going to go to 0 because negative 8 plus 8 is 0, and 0 times a is 0. And I'm left with b times negative 8 plus 3. All right, well, negative 8 plus 3 is negative 5, so I'm going to end up with an equation, negative 5b equals, and then somebody plug this into the calculator for me and tell me what we get. Negative 35. So to solve for b, I would just divide both sides by negative 5, and I get b is equal to 7. Then I'm going to pick another number for x to be. So I'd say if x is equal to, let's try negative 3, because that way this b will go to 0. Then we get 13 times negative 3. We're just plugging in the negative 3 in place of x. Plus 69 is equal to a times negative 3 plus 8. So that's going to be a positive 5a equals what? Plus negative 39, so that would be 30. Then we would divide both sides by 5, and that would give us a is equal to 6. So that means that the partial fraction decomposition of 13x plus 69 over x plus 3 times x plus 8 is going to be equal to 6 over x plus 3 plus 7 over x plus 8. And why is that useful? Well, because if I asked you to integrate 13x plus 69 over x plus 3 times x plus 8 dx, I could say that that's equal to the integral of 6 over x plus 3 dx plus the integral of 7 over x plus 8 dx. And here I could do a u substitution. If I let u be equal to x plus 3, what is du going to be? Let me show the steps. If I let u be equal to x plus 3, du is equal to what? Just dx. And over here, if I let u be equal to x plus 8, what is du? It's just dx. So here I would end up with then the integral of, I can pull the constant of 6 out, and I just get du over u. And here I could pull the constant of 7 out, and I get du over u. And what is the integral of du over u? It's just the natural log of u. But what was u equal to? I'll go ahead and plug that in. So this is going to be 6 times the natural log of x plus 3 plus 7 times the natural log of x plus 8. And because we didn't have bounds on the integral, we would say plus c. Then we can use the property of logs to rewrite this. When you have a constant in front of a log, what do you do with that constant? Right, we move it up into the power. Remember the power rule for logs? If you have the natural log of x raised to a power of n, you could rewrite that as n times the natural log of x. Also, if you have the natural log of x times y, that could be rewritten as the natural log of x plus the natural log of y using the product rule. So that means that I could use these two rules together to rewrite this problem or this answer as the natural log of x plus 3 to the 6th times x plus 8 to the 7th. And I'd want to take the absolute value of that, because if this ends up being a negative expression, I have to have a positive value that I take the natural log of. So that would be our final answer. But trying to get that from this was infinitely more difficult, and that's why we use something called partial fraction decomposition. So how partial fraction decomposition works is you need to expand the denominator like this, where if you have a linear factor, you're going to have a constant on top. But if you have a quadratic factor, we're going to put a linear factor on top. So this is the method of partial fraction decomposition, and this works for proper fractions. The key word here is proper. That means that the degree of the numerator is less than the degree of the denominator. So if your fraction is not a proper fraction, the first thing you're going to want to do is do long division on the polynomials to simplify. We'll see an example in a little bit where we do that. So when we expand using partial fraction decomposition, we're going to let x minus r be a linear factor of a function. If we have that factor raised to a power where m is the highest power of that factor, then to expand that, I'm going to have each one of those factors with a different constant over it from the first degree all the way to the nth degree. So for example, if I had 1 over x plus 2 cubed, I would expand that into a over x plus 2 plus b over x plus 2 squared plus c over x plus 2 cubed. For each power, whatever the degree is or the multiplicity of that factor, you're going to have to expand all the way up from the first degree, second degree to the third degree. If you have a quadratic factor that is prime, meaning it can't be factored any further, then on top, instead of putting a constant, we're going to have to put a linear factor, which would be like ax plus b, cx plus d. And the same thing that worked with the powers here is going to work with the powers here. If that quadratic factor is raised to a power, you're going to have a different linear factor for each one of those factors. So this means that if we had something like 1 over x squared plus 4, because the sum of two squares doesn't factor any further, I would expand this into ax plus b over x squared plus 4 plus cx plus d over x squared plus 4 squared plus ex plus f over x squared plus 4 cubed. Once you have your factors expanded, you have your fraction expanded, then you're going to plug in numbers for x to generate a system of equations and solve for a, b, c, d, e, f, g, whatever you have on top. And you can let x be any number you want. Typically, you want to pick numbers where the factors go to 0. But in something like this, that factor is never going to be equal to 0. So we would just pick out different numbers and try to pick small numbers so the arithmetic is easy. And so we would set the original fraction equal to all these numbers and then multiply both sides of the equation by the least common denominator to get an equation without fractions. That's what we did up here. We expanded this first, and then we multiplied both sides of the equation by the least common denominator, and what that did was it got rid of the fractions, so I just had an equation like this. And then when I plugged in my numbers for x and solved for the variables. It's going to make more sense as we get into solving problems. So let's look at example 2. They ask us to expand the quotient by partial fractions. So the first thing I need to do is expand this. Is this going to be a constant on top, or is it going to be like ax plus b? X plus 5, is that a linear factor? Yes, it is. The fact that that's squared, this is a linear factored square. That 2 right there is the multiplicity of the power. So since it's a linear factor, the degree of the numerator is going to be 1 less, so I'm going to just have a constant on top over x plus 5. And because that x plus 5 is squared, I need one more of these, and I'm going to write that as x plus 5 quantity squared. Once I have this expanded, what's my next step going to be? Multiply both sides of the equation by the least common denominator. My least common denominator is going to be x plus 5 squared, and this has to be distributed across to both of these. Well, when I multiply this left-hand side of this equation by x plus 5 squared, those are going to cancel out, and I'm left with x plus 8 equals, and then when I multiply the first term here by x plus 5 squared, that x plus 5 will cancel with one of those x plus 5's, and I'm left with a times x plus 5. And here both of these are going to cancel out, and I just get plus b. So our next step then is going to be to pick numbers for x and solve for a and b. So we can say if x is equal to, what do you want x to be equal to? Negative 5. If x is equal to negative 5, then we get negative 5 plus 8 equals, that's going to be 0, and we get b. So that means that b is going to be equal to negative 5 plus 8 is 3. Now I know a number for b. Then I've got to pick another number for x. What do you want to let x be equal to now? 0 is a good number. Arithmetic is easy with zeros, right? If it's available, use it. If x is equal to 0, then we get 0 plus 8 equals a times 5, and we said b was equal to 3. So to solve this, I would get 5a equals 5. So what is a equal to? A equals 1. That means that x plus 8 over x plus 5 squared can be expanded into 1 over x plus 5 plus 3 over x plus 5 squared. And this would be the partial fraction decomposition of this expression. Now remember I said that we have to have a proper fraction before we start. Is this a proper fraction? No, it's not, because the degree of the numerator is greater than the degree of the denominator. So the first step in this problem is to reduce this fraction. Does everybody remember how to do long division with polynomials? You probably saw it in pre-cal, so you've probably slept since then. So let's review that. So this is going to be scratch work. So we take the denominator and we divide it into the numerator. Now if you have a missing power, you want to have a 0 for that missing power, 0 term for that missing power. So we have x squared minus x divided into 10x cubed minus 10x squared plus 0x plus 3. You want to have every term for every power of x. And when you divide this, you just look at the first terms. So what I'm going to do is I'm going to look at 10x cubed divided by x squared. Notice that 10x cubed divided by x squared is going to be equal to 10x. So we're going to put that 10x up on top. And then when you do long division, you have to multiply by what's out in front and then subtract that product right here. So 10x times x squared gives me a 10x cubed. And then 10x times negative x gives me a minus 10x squared. And then we need to subtract this. So I'm going to subtract that, and subtraction means that I'm going to change the signs and add. And that's going to give us, well, both of these terms go away, and that goes away. That just leaves us with 3. Does x squared divide into 3? No, it does not. So that last term I'm going to write as 3 over my x squared minus x. So that means that I can take my problem, the integral of 10x cubed minus 10x squared plus 3 divided by x squared minus x dx, and I can rewrite that as the integral of 10x plus 3 over x squared minus x. And don't forget your dx. So the 10x I can integrate pretty easily. This one might be problematic, but notice I can factor an x out of that denominator, can't I? So I'm going to come along and do some more scratch work here. I want to do partial fraction decomposition on this last term. So that last term I could write as 3 over x times x minus 1. And when I expand this using partial fraction decomposition, what am I going to write? What am I going to expand this to? I have two linear factors here, so that's going to be a over x plus b over x minus 1. Are there any questions about how I came up with those? When you do partial fraction decomposition, you want to factor the denominator, and then you just put constants over each one of those factors. Now I need to solve for a and b. What is my next step going to be? I want to get rid of the fraction, so I'm going to multiply both sides of the equation by the least common denominator, which is x times x minus 1. What you do to one side of the equation, you have to do to the other. Well, when I do that, this entire denominator is going to cancel out here, and that's just going to leave me a 3. Then I'm going to distribute this least common denominator to both of these terms, and then the x is going to cancel here, and that's going to leave me a times x minus 1 plus b times what? B times x. What's my next step towards solving for a and b? Because that's our goal. We want to know what numbers we can plug in place of a and b so I can expand this fraction over here. We want to pick numbers to plug in for x so I can get equations in terms of a and b. What number should I use for x? 1. All right, so if x is equal to 1, then what am I left with? 3 equals b. Boom, we've solved for b. What other number can I use? 0. 0's good. If x is equal to 0, since there's no x over here, I'm just going to write down the 3 equals 0 minus 1 is negative 1. Negative 1 times a is negative a. And I plug in a 0 for x, that b goes away. So I have 3 equals negative a, which means a is equal to negative 3. So that means that this fraction, 3 over x times x minus 1, can be written as negative 3 over x plus 3 over x minus 1. So that's what I'm going to do. I'm going to rewrite that expression up here, and I'm going to replace this expression with this expression. So that means that this integral can be rewritten as the integral of 10x dx minus, and there's already a 3 here. Oh no, that 3 was taken into account whenever we rewrote this. So I don't factor that 3 out. I'm going to be looking at these 3. So I'm going to get minus 3 times the integral of dx over x plus 3 times the integral of dx over x minus 1. Does everybody see how I did that? These terms right here came from this down here. I just pulled the constant that was on top out in front of the integral. Now we're ready to integrate. What do you get when you integrate 10x? Add 1 to the exponent, divide by the new exponent. What's the integral of dx over x? It's the natural log of x. And what do I get when I integrate dx over x minus 1? 3 natural log x minus 1, and then put plus c. So now I want to simplify this. That's going to give us 5x squared, and then I'm going to say plus the natural log of x minus 1 cubed over x cubed. And don't forget the plus c. Is everybody okay with how I use properties of logs to rewrite this? That 3 went into the exponent. A negative in the exponent kicks it into the denominator. Then I use the product rule here. That 3 became the power on the x minus 1. Are we okay with that? So let me just do some scratch work on the steps on how I got to this point. To go from this to this, I'm going to show the work. Okay, so negative 3 natural log x plus 3 natural log x minus 1 can be rewritten as the natural log of x raised to the negative 3 plus the natural log of x minus 1 raised to the positive 3. Then we use the product rule. When I add two logs together, that means I could rewrite that as a single log of the product of each of these terms. So that's x to the negative 3 times x minus 1 to the third. We don't want to leave the negative exponents in there, so that would give us the natural log of, to make the negative exponent positive, I would just kick it into the denominator, and I'm left with x minus 1 cubed over x cubed. Because when the exponent is negative in the numerator, once you move it to the denominator, it becomes positive. So that's how I came up with this right here. That's what this scratch work is for. But our final answer is going to be this expression right here. Let's look at example 4. Here we're asked to express the integrand as a sum of partial fractions and then evaluate the integral. We don't want to try to evaluate this integral without doing that. And I don't know why I picked a problem with s's in there. I'm going to change this problem. I'm going to change the s's to x's. So we're going to call this the integral of 14x plus 14 over x squared plus 1 times x minus 1 cubed dx. Is this a proper fraction? Sure, the degree of the numerator is 1 and the degree of the denominator is 5. So what I'm going to do is I'm going to take the 14x plus 14 and I'm going to put that over x squared plus 1 times x minus 1 cubed. Does this quadratic factor reduce? Can I factor it further? No, because the sum of two squares does not factor further. This is the first problem we've had now since I've talked about it, where we have a quadratic factor that's prime. When I write this out in its expanded form, I've got to have a linear factor on top. So that linear factor is going to be ax plus b, and that's going to be over x squared plus 1. Now x minus 1, is that quadratic, cubic, or linear? I'm not looking at the multiplicity, the power on it. I just want to know about x minus 1. So this x minus 1 is a linear factor, but it's raised to the third power. That means I'm going to need 3 factors written out or expanded out here for this one factor. Because it's a linear factor, I just need a constant on top. So I'm going to the next letter in the alphabet. So that's going to be c over x minus 1 to the first power. And then I'm going to do d over x minus 1 to the second power. A, B, C, D, E over x minus 1 to the third power. We have to have a constant on top for a linear factor and a linear expression on top of a quadratic factor. Whatever the multiplicity is, we've got to expand it, taking into account each power up to the maximum power. Are we okay with how we expanded this? No? What part is confusing? A question was asked about how we came up with these middle terms because the student just sees this factor, which is on the first one, and this factor, which is on the last one. How do we come up with the ones in between? Well, whenever you're doing partial fraction decomposition, if you have a factor that's raised to a power, you have to have every single power from 1 all the way up to that highest power. This expression right here is x minus 1. That x minus 1 is being raised to the third power. So I've got to start out with x minus 1 to the first power, then to the second power, and then I stop when I get to the third power. So this was the first power, the second power, and then finally the third power, because that was the power that I had in the problem. When we looked at the rules back here, that's what I was trying to explain. Whenever you have a factor that's raised to a power, you have to have every single power from 1 all the way up to that highest power. That's why I said if this was my fraction that I needed to expand, I want to start out with x plus 2 to the first power, then x plus 2 to the second power. I got to keep going because I got to go all the way out to the third power. Does that make sense now? You're probably wondering, why does it work that way? I'm more concerned that you remember the way that it works than why it works that way. We just know that it works that way, that you have to have each one of those factors taken into account. Now, when we simplify this, some of those factors are going to go to 0. So let's continue. Picking up where we left off now. Now we're ready to solve for A, B, C, D, and E. Now that's a lot of letters. We're going to have a lot of equations. So our next step, once we have this expanded, is we're going to multiply everything by the least common denominator. And I'm just going to write LCD, just because I don't want to write all that stuff out again. And what I'm left with on the left is just going to be 14x plus 14. Now when I multiply this first fraction, because I have to distribute that LCD across here to each one of these fractions, I'm going to be left with the factor ax plus b times what? The x plus 1 squared is going to cancel out. I'm left with x minus 1 cubed. When I multiply the least common denominator by c, the x minus 1 to just one of them is going to cancel out, and I'm left with x squared plus 1 times x minus 1 squared. Because this x minus 1 will cancel with one of those x minus 1s and leave me 2 of those x minus 1s. For the next term, I get d. Now I've got x minus 1 squared, so I'm going to have this first factor times that to the first power. So that's going to be x squared plus 1 times x minus 1 to the first. And then I get e times the x minus 1 cubed is going to cancel out when I multiply this by the least common denominator, and I'm left with x squared plus 1. Okay, so now I've got to pick numbers to plug in and solve for A, B, C, D, and E. That's 5 variables. Odds are good we're going to need 5 equations. So I'm going to pick a number for x. What number do you want to pick for x? Is there a number that you think might make things go away? If x is equal to 1, then we have 14 times 1 plus 14. 14 plus 14 is 28 equals, this is going to be a plus b times 1 minus 1 goes to 0. So every term up here that has an x minus 1 in it, that's going to go to 0. So this first term's going to go away. The next term's going to go away. This has an x minus 1. I'm just left with e, aren't I? I'm plugging in 1 for x. 1 squared is 1 plus 1 is 2. I get 2e. So if 28 is equal to 2e, what is e equal to? 14. So now I can use a number for e. We need another number to plug in. I would want to start with 0. 0 makes the arithmetic easier. So we're going to let x be equal to 0. And when I do that, that's 14 times 0 is 0, plus 14 is 14, equals, this x is going to go to 0, and I'm left with just a b times what? 0 minus 1 is negative 1. Negative 1 cubed is negative 1. Plus, plug in a 0 for x. So that's going to be 1 times, and a negative 1 squared is 1. So that's just going to give me c. Watch the arithmetic. I'm plugging in a 0 in place of x. So that when I plug in a 0 here, that's going to give me 1. And here, that's going to give me a negative 1 squared is 1. 1 times 1 is 1. And 1 times c is c. Plus, plug in a 0 here. That's going to give me 1 times negative 1. So that's going to give me a negative d. And then e we said is 14 times 0 plus 1 is 1. So that's just going to be 14. Now we can subtract 14 from both sides of the equation, and I'm left with the equation negative b plus c minus d equals 0. That's one of my equations. So I've let x be 1. Now I want to let x be negative 1. Let's just keep the number small to keep the arithmetic easy. If x is equal to negative 1, I go back up here. Negative 1 times 14 is negative 14, plus 14 is 0. That's going to give me let's do the number part first. So that's going to give me a negative 1 minus 1 is negative 2. Negative 2 cubed is going to give me negative 8. So this is going to be negative a plus b times negative 8. When x is equal to negative 1 here, that's going to give me a negative 1 squared is 1 plus 1 is 2. Negative 1 minus 1 is negative 2. Negative 2 squared is 4. So this is going to give me 2 times 4 is 8. So that's just going to be 8c. Negative 1 squared is 1 plus 1 is 2. Negative 1 minus 1 is negative 2. 2 times negative 2 is negative 4d. And then e we said is 14. And negative 1 squared is 1 plus 1 is 2. So that's negative 14 times 2. And I'm going to distribute this 8 across. So that's going to give me a positive 8a minus 8b plus 8c minus 4d equals negative 28. This is not a difficult process, but it is a tedious process. All right, we need more equations because we've got 1, 2, 3, 4 variables. We need a minimum of 4 equations in order to solve a system of equations with 4 variables. So let's go with 2 and negative 2 just to keep the arithmetic as easy as possible. If x is equal to 2, 14 times 2 is 28, plus 14 is 42, equals, this is going to give us 2a plus b times 2 minus 1 is 1, 1 cubed is 1, so I'm just going to put times 1. And 2 squared is 4, plus 1 is 5. 2 minus 1 is 1, and 1 squared is 1. And then I have d, and then 2 squared is 4, plus 1 is 5, times 2 minus 1 is 1. And then e we said was 14 times 2 squared plus 1 is 5. So what I'm going to do is I'm going to write this as an equation, move the constants to the one side and leave the variables on the other. So that's going to give me 2a plus b plus 5c plus 5d equals, and 14 times 5 is a really big number, 70. So I would say 42 minus 70 is negative 28. So that's our third equation. I need one more. So we're going to let x be equal to negative 2. So going back here, 14 times negative 2 is negative 28 plus 14 is negative 14. Negative 2 times a is negative 2a plus b times negative 2 minus 1 is negative 3, and negative 3 cubed is negative 27 plus c, and negative 2 squared is 4 plus 1 is 5, and negative 2 minus 1 is negative 3 squared is 9. And then we have d times negative 2 squared is 4 plus 1 is 5. And negative 2 minus 1 is negative 3. And e we said was 14 times negative 2 squared is 4 plus 1 is 5. Setting the variables equal to a constant, I'm going to be left with negative 2 times negative 27 is a positive 54a minus 27b plus 45c minus 15d equals, and this is going to be 70 subtracted, so that would be minus 84. Now we're digging back into some algebra stuff. So I've got a system of equations, and I'm going to take all 4 of these underlined equations and write them. All right, so these are the 4 equations that we came up with. We're not going to solve these by hand. We're going to let our calculator do the heavy lifting. Do y'all remember how to set up a matrix in your calculator and use your calculator to solve the matrix? First of all, we need to write down the coefficients. So in our matrix, I've got 4 equations and 4 variables. So the first column of numbers are the constants on A. The next one would be B, then C, then D. And then we need equals, and then we have our numbers out here. So the matrix that I'm going to set up on my calculator is going to look like this. It's going to be 0, negative 1, 1, negative 1, 0, 8, negative 8, 8, negative 4, negative 28, 2, 1, 5, 5, negative 28, and then 54, negative 27, 45, negative 15, negative 84. So let's get our calculators out. All right, to find the matrix on your calculator, you're going to hit second, second, and then matrix is listed right above the inverse button, so that's going to be second x inverse. And what we're going to do is we're going to edit a matrix, and I want to edit matrix A. The first thing you got to do is put in the size of the matrix. The first number is the number of rows, so we have 4 rows. And then the next number is the number of columns, and we have 5 columns. So this is going to be a 4 by 5 matrix. Then we're just going to enter these numbers into our matrix that we have written over here. And I'm just typing in the numbers going across the rows. And then when I hit enter, it drops me down to the next row. So that's going to be 8, negative 8. Double check your numbers. While this is not difficult, it is very unforgiving if you type one thing in wrong. It looks like my numbers are good, so I'm going to hit second quit. Now, in order to get your calculator to solve the matrix, we got to go back into the matrix function, and we're going to do the math on it now. And what we want to do is the row reduced echelon form, or reduced row echelon form, that's letter B. And then we got to tell the calculator, well, what matrix do you want to find the RREF of? Well, with names highlighted, I'm going to plug in matrix A. Close the parentheses or not, it'll still give you the answer. And this is our answer. Now, how you read the answer is like this. Remember, we said that this first column corresponded to the A's, B's, C's, D's. We had an equal sign and then a number. So what that means is A is equal to 0. B is equal to 7. C is equal to 0. And D is equal to negative 7. The calculator is your friend for these problems. The hardest part, I think, was setting up or getting the equations to plug into the calculator. And if you have a lot of variables, when you do this partial fraction decomposition, you're going to have to use the matrices on your calculator to help you with the arithmetic. The question was, what did we do about E? The answer is we didn't have to plug e into the calculator because right up here we already found what e was. E was 14. So that means that my integral, 14x plus 14 over x squared plus 1 times x minus 1 cubed dx, can be written as, what did we say a was? A we said was 0. So that term is going to be a 0. And b was equal to 7. So b was equal to 7. And b is over this factor x squared plus 1. C was equal to 0, so I don't have to worry about this fraction because C was 0. And D was equal to negative 7, so that means I'm going to have minus 7 over x minus 1 squared. And then E was 14 over x minus 1 cubed dx. We now need to evaluate the integral. Thanks to the magic of OneNote, I'm just going to copy this expanded form down and then paste it down here. And so this is the integral that we have to evaluate. And what I'm going to do is I'm going to expand this out into 3 different integrals. That's going to be 7 times the integral of dx over x squared plus 1 minus 7 times the integral of 1 over x minus 1 squared. That's actually a dx over x minus 1 squared plus 14 times the integral of dx over x minus 1 cubed. To evaluate these last two, I can do a u substitution. What am I going to let u be equal to? X minus 1. What is du equal to? Dx. That's going to make solving these last two rather easy. How am I going to solve this first one? This is what we learned last time. I can use trig substitution on this one, can't I? Unless you already have it memorized. This is tan inverse x. If you already have it memorized, you don't have to do the trig substitution. If you don't have it memorized, you've definitely got to do the trig substitution. So what I'm going to do to make this a little easier is I'm going to work with each one of these one at a time and then come back at the end and put them all together for our final answer. Are y'all okay with that? So I'm going to call this one 1, 2, and 3. So working with number 1 first, I'm going to look at 7 times the integral of dx over. Now, there's not a radical here. How can I rewrite that with a radical? Because I need the radical there for my trig substitution. I could write this as the square root of x squared plus 1 squared, couldn't I? Then I'm going to set up my triangle. And there's my angle theta. There's my 90-degree angle. What is the hypotenuse going to be? It's going to be the radical because there's a sum between those terms. So that's x squared plus 1. What is the opposite side going to be? X. And what is the adjacent side going to be? 1. So now to do our substitution, we're going to let x over 1 be opposite over adjacent, and opposite over adjacent is equal to tangent. What is dx going to be? Secant squared theta d theta. The other piece I need to know is the radical. Well, if I put the radical over 1, that's hypotenuse over adjacent, and hypotenuse over adjacent is equal to which trig function? Secant. So putting all this together, that's going to give us the integral of secant squared theta d theta over secant squared, because that radical was being squared. Well, the secant squares are going to cancel out, and that's going to give us the integral of 7 times d theta. Well, when you integrate 1 d theta with respect to theta, you get 7 theta. I know it's a plus c, but I've got 3 of these. I'm going to put the plus c on my final answer. Y'all okay with that? How do I figure out what theta is when I look at my triangle? I solve this equation for theta. So to get the theta by itself, I'm going to take tan inverse of both sides of this, and I get this is equal to 7 times tan inverse x. The second integral here was negative 7 times the integral of dx over x minus 1 squared. And I said we can use this u substitution, so I'm going to rewrite that as negative 7 times the integral of du over u squared. But that's going to be u to the negative 2, isn't it? Because this was what u was equal to. And when I integrate, I don't want du over u squared. I want to rewrite that u squared as u to the negative 2, so I can then use my power rule to integrate. So that's going to give us negative 7 times, I add 1 to the exponent, and that's going to make this a negative 1 times u to the negative 1. But I don't want to leave my final answer in terms of u. This is going to end up being 7 times 1 over x minus 1 to the first. The question was, where did this negative 1 come from? Well, when you integrate this, we add 1 to the exponent. Negative 2 plus 1 is negative 1. And then we divide by that new exponent. Well, dividing by negative 1 is the same thing as multiplying by negative 1. All right, on number 3, we have 14 times the integral of dx over x minus 1 cubed. Using that same u substitution, I'm going to rewrite this as u to the negative 3 du. And when I integrate that, that's going to give me 14 times. When I add 1 to negative 3, that gives me a negative 2. So this is going to be multiplied by a negative 1/2 u to the negative 2. And that's going to give us negative 7 times 1 over x minus 1 squared plus c. So putting all 3 of these together for this final answer, we're going to end up with a final answer of 7 tan inverse x plus 7 over x minus 1 minus 7 over x minus 1 squared plus c. And that would be our final answer. It was a lot of work, but it wasn't terribly difficult work. It might have been terribly tedious work for this part, but once we expanded that, there's no other way that we could evaluate this integral other than using partial fraction decomposition. It's just too complicated. So partial fraction decomposition can be used to take a very difficult problem and break it down into a much more manageable problem. That's the strength of the partial fraction decomposition. And that's the last problem that we have for today.